Alright, welcome back. Today we're going to be talking about double replacement reactions. In a double replacement reaction, we are going to be swapping one element in each compound to a different compound. So we're forming two new compounds in this reaction. What do we look for to identify a double replacement reaction? When we're looking for two compounds on each side of the reaction. So if you look up here, we have silver nitrate and we have sodium chloride both on the left side, the reactant side. They're both compounds. When we look on the right side, we have sodium nitrate and we have silver chloride. They are both compounds. So everything in this reaction is a compound. They're a compound because they have two elements bonded together. So that means this is a double replacement reaction because we have no elements in this reaction at all. It's individual elements, I should say. They're all in compounds. Okay? So what's happening in a double replacement reaction? Well, you could think of it in two different ways. You could think of it as the cations are going to be swapping, or you could think of it as the anions are going to be swapping. It doesn't matter. But when we look at this, we have the silver is with the nitrate in our reactants. In the products, the silver is with the chlorine. So we're just thinking of this as we're just doing a little switcheroo here. We're doing a swap. All right, so a swap between two of them, a double switch. Okay? When we balance this, nothing is different. So it's the same as what we've always done. We just start off by saying, okay, we have silver, we have nitrate, we have sodium, and we have chlorine. When we put our polyatomic ions out to count them, we want to try our best to keep them as a polyatomic ion and not write them out as nitrogen and oxygen. In this case, nitrate is the same on both sides, so this is a good sign, so we don't have to do anything here. We can just leave it be. Alright, now we count them up on each side. One silver, one nitrate, one sodium, one chlorine. Look at that. It's already balanced. So sometimes you'll get equations that are already balanced. This happens a lot when the charges of the cation and anion are all ones around the board, and that's what we have here. All the charges of these as ions are 1. So there's no coefficients. Okay, so you have two options. You can leave it blank because that's what it is. When you write it out, you wouldn't write the 1 in front. If you want to write a 1 in front because it just helps you feel better, put a 1, whatever. Just know that when you write it out on a piece of paper for real, there's no 1 in front, right? Because if I wrote it, that means there has to be one of them, right? Alright, moving to the next one. One take, everybody knows the rules. A little bit lower. Okay, there we go. Alright, same deal. This is double replacement reaction because we have two compounds on each side. So we'll start balancing this the same way. So we have iron, we have bromine, we have barium, and then we have hydroxide. And again, we're keeping the polyatomic ion the same because it's the same on both sides, which is fantastic. So we look at our iron, we have 1 on each side. Our bromine, we have 3 on the left, 2 on the right. Barium, 1 on the left, 1 on the right. Hydroxide, 2 on the left, and 3 on the right. Okay, now we can begin to balance it. So this is the same deal with the 2s and the 3s, right? So the least common multiple is 6. Like we've seen this many, many times already. So if we want to get to 6, we need to multiply by the other number. So for 3 to get to 6, we need to multiply by 2. For 2 to get to 6, we need to multiply by 3. Oh, and I put equals. We need to multiply by 3. And that gets us 6. Okay, so when I multiply by 2, where does it go? Right there in front. And I multiply by 3. Where does this go? Right in the front. 3. Okay, so that balances out our hydroxide. Now, what did that do to everything else? So we put a 2, because this 2 goes to the iron and the hydroxide. It made our iron to be 2. Our barium, it made it to be multiplied by 3. So we put multiplied by 3 is 3. Okay, now we can balance our barium. We have 3 on the left, 1 on the right, so we have to multiply by 3. That gets us 3 here. Done. Bromine. Now what did that do? We multiplied by 3, so that 3 goes to the barium and the bromine. So when we have a 3 and we have a bromine already like this, Br2, diatomic bromine, what is this saying? Well, it's saying we have 3 Br2s. Br2, Br2, and then we have a Br2. We have 3 of those. So how many bromine total are here? There's 6 total. So that's why it ends up to be 6. So multiply by 3 gets us to be 6. Alright, on the left side, I have a 3 already. What do we have to do to get to 6? Multiply by 2. Okay, that's balanced. Put a 2 up there. That balances our iron as well to be 2 iron on each side. Okay, so they get 2, 3, 2, 3 for balancing that. Alright, last one. This one is the longest one so far. Has the most elements in it. Okay, when we do this, start at the top. Calcium. Phosphate. Now, when I look at this phosphate, what do I notice? It's a phosphate on the left, but is it on the right? It is not. So because it's broken apart, I'm going to write this out separately as phosphorus and oxygen. Now I come to SiO2, I'm going to write my silicon out, but I already wrote oxygen, so I don't need to write it again. I'm just going to add it in there. And then we have carbon. Okay, now I'm going to count them up. So calcium, we have 3 on the left. Phosphorus, we have 2, right? Because this 2 goes to the oxygen and the phosphorus. So we have 2 phosphorus. How many oxygen here? 4 times 2 is 8. And because there's 2 spots for oxygen here, I'm going to put 2 separate markers. So when we go to SiO2, I'm going to put the 2 there, knowing that I have 8 oxygen at one place, 2 in another place. My total is 10. I'm going to have to come back to this on a race, but this is just showing me that I have 2 separate locations for this oxygen. Okay, then I have carbon as one of them. On the right side, calcium, I got 1. Silicon, I got 1. Oxygen, there's 3 in the first slot. Phosphorus, there's 1. Carbon, there's 1. Oxygen, there's 2 in the second slot, so my total is 5. Okay, so for this, what the heck do I do to start? So, what I like to do to start is I like to start with the biggest compound with the most elements in it. So, we're going to start with the calcium phosphate because there's 3 calcium, 2 phosphorus, and 8 oxygen. This has the most elements, so we're going to start there. This isn't just as easy as saying, okay, there's 5 oxygen and 10 oxygen, and we're going to multiply by 2. Because the oxygen are split up, it makes this a little bit more tricky. When we look at our biggest compound, or our compound with the most elements, we always want this to be 1 if we can. So I'm going to assign this to be 1 on the left because we have the most things there. If we assign that to be 1, that'll limit the amount of multiplication and the multiple steps we're going to have to do. So we're going to assign that to be 1, and we're going to balance everything else based on this being 1. So if I have 3 calcium on the left, how many calcium on the right do I have? Well, I have to have 3. So I'm going to put that 3 there. So by assigning that, I know this is done and this is done, and I can't touch those 2. Now everything else is going to balance around those 2. So this gives us a little bit of structure. What did this do to the right side of the equation? Well, it gave us 3 calcium. What else did it give us? It also gave us 3 silicon, because this 3 goes to each one, right? So it gave us 3 silicon. Okay. What did that do to the left? We had to put the 3 there too, right? Because that means our silicon needs to balance. So our silicon is balanced and our calcium is balanced. Okay. What else can I do? Well, we have 2 phosphorus on the left. How many do we have to have on the right? 2. So we have 2 phosphorus. So, really quickly, we've already narrowed this down to 2 slots left. That's it. So by assigning the 1 to our largest compound, we were able to make this hard-looking problem pretty easy. And now we're just left with balancing the oxygen. So I'm going to erase the total numbers and update this based on the numbers we've given. So on the left side over here, it's still the same. So this 8's the same. When we look at this, we did 3 times 2. So we multiply that by 3, and we have 6. So our total on the left is 8 plus 6. What's 8 plus 6? 14. Okay. Now we look on the right. We had 3 and we multiplied that by 3, and that gave us 9. 3 times 3 is 9. And then we have 2, and that's 11. So we cannot touch the left side oxygens. So it has to be 14. We can't touch the top on the right side. So the only oxygen we can touch is this 2 right here. That's the only thing we can touch. We have to multiply this 2 by some number in order to get the left side oxygens, which are 11 right now, and 14 to balance. So what I need to do is I need to disregard this 11. I'm going to erase it, and I'm going to say, okay, I have 9 oxygens already, and I have 14 on the left. How many more do I need to get to 14? So I have 9. I need 14. I can only multiply something by 2 to get that. So we have 14 on the left, and that equals 9 plus 2x. Because this 2 is here, and we want to know, okay, what am I multiplying that by? So this is an equation you can use to sort of solve this out. So 14 minus 9 is 5, equals 2x. Divide by 2, x equals 5 halves. So our coefficient for this, in order to get these oxygens balanced, is going to be 5 halves. You can multiply by fractions. It doesn't matter because we're talking about moles of a number. We're not taking 5 halves carbon dioxide. We're taking 5 halves of a mole. It's like taking 5 halves of a cup or something like that, you know? It's not just cutting one of the molecules in half. Okay. When we do 2 times 5 halves, what does that do? Well, it takes away the 2. Now I just realized that this is off the screen. So this is what I was talking about when we were looking at this equation. We had 14 equals 9 plus 2x. You could have subtracted 9 from the 14 to get you 5 equals 2x. Divide by 2. Your x equals 5 halves. When we multiply by it with a coefficient, we're going to do 2 times 5 halves. So when we do this, these 2 go away, and it just equals the 5. So that allows us to get 9 plus 5. That says, okay, now we have 14 oxygens on the right. So we multiply this by 5 halves, and that balances it out. Now, on the right side, we now have 5 halves oxygen. I mean carbon. 5 halves carbon, because this goes here to the carbon and there to the oxygen. So what do I have to do to the carbon on the left? I also have to do 5 halves. Okay, now we are balanced. So let's go back to see the whole thing. There we are. Oh, not quite on the screen. Okay, we're done on the screen. Okay, so this one's a little bit trickier because we had to use fractions as a coefficient. So that doesn't make it that much harder. We just have to think around it. You don't have to solve it the same way I did. You don't have to write an equation out. You don't have to do some algebraic function thing. Doesn't, as long as you can balance the number of elements on each side, that's fine. Now, if we were to write this out with no fractions, what would we do? We'd multiply everything by 2. And it would still be the same. So we can make this 2, we could make this 6, we could make this 5, we'd make this 6, we'd make this 4, and we make this 5. So if you have 2, 6, 5, 6, 4, 5 as your coefficients, that works too. It doesn't matter. So you can have either one of these. You can have the 1, 3, 5.5, 3, 2, 5.5, or 2, 6, 5, 6, 4, 5. Doesn't matter. I'm an auctioneer now. It's my second job from now on. Okay. So this is one of the hardest double replacement reactions you have to solve. Not many more harder than this one. So if you can do this one, you'll be good at solving double replacement reactions.